Good morning, sirs. Today we would like to give you an insight into our project, design of a robust quadcopter controller for stable landing. Quadcopters has become increasingly popular among the general public and the industries in recent years. While the public may use them for entertainment purposes, industries have been utilizing drones in their workforces. For example, we can point out agriculture, logistics, surveying, and cinema industry as a few. Why robust control? So while the quadcopters are becoming increasingly common, it needs to have the ability to withstand sudden changes in the environment or uncertainties while maintaining the control even under those circumstances. If we list out few disturbances within the quadcopter, we can point out two categories, which are internal and external disturbances. While internal disturbances can be reduced by computing a more complex model, external disturbances such as wind varies in a given environment. As we are focusing more on wind disturbances, our main focus is on the landing portion of the quadcopter operation, because at that stage wind can become turbulent and can result in malfunction of the quadcopter. For example, as shown in this scenario, while the quadcopter is hovering in air, it is subjected to a lateral wind force disturbances, and when close to the ground, it can face disturbances generated by the ground effect. When considering about the modeling of the quadcopter, we can use a non-linear model which is more complex and a linear model which is not complex, but the linear model does not represent a realistic quadcopter model. Here comes the 12 nonlinear equations that we have derived for quadcopter dynamics. And this shows the simplified version of those nonlinear equations used in Taylor expansion. Comparing those two models, we have chosen the nonlinear model because it represents the quadcopter more closely and gives us the flexibility to work with multi-input, multi-output systems. To simulate the landing path, we have simulated the trajectory generator which uses the minimum jerk method to get us an optimum path which the quadcopter can take when it is given points to follow. Here we are trying to simulate a path for both hovering and landing, where the drone starts from a high point and makes a route above and descends from that path to the land. This is the 3D view of that path. Then we have simulated the wind disturbances acting along that path. We modeled that using three varying wind speeds acting on the quadcopter, which results in three varying forces acting on the quadcopter. As we have mentioned previously, the trajectory drone takes consists of hovering and landing paths, where the wind disturbances acting along that path may vary too. During hovering, wind forces along x and y axis are dominant, and during landing, the wind forces acting along the z-axis is dominant because of the ground effect. Those varying wind disturbance forces can be represented as in these graphs. These are the specifications of our drone in simulations, and we are simulating the given scenario using PID controller and sliding mode controller. As we can see here, PID controlled drone struggles to follow the desired path under the given wind disturbance profile. Now let's move on to the simulation done using this SMC controller. As shown here, while under the same disturbance profile, SMC controlled quadcopter almost exactly follows the given path. Here we have shown the comparison of position data generated in the both simulations. And here we have shown the comparison of velocity data generated in both simulations. This proves the SMC-based nonlinear model control structures are more superior than the commonly used PID-controlled quadcopters for robust control in stable landing situations. That's the end of our demonstration. Thank you.